Okay, so this is lecture 3C. Next topic is the method of images, and I'll briefly describe two classic cases which is allowed because of the uniqueness theorems that we have discussed so far. The agenda is to the use of the license given by uniqueness theorems to solve problems using method of images. I say license because uniqueness theorems give some freedom to choose any method to come up with a solution. And if the solution obeys the conditions specified by uniqueness theorem, then it's a valid solution. So method of images is a popular method of solving problems by using the as if a conductor or a material is like a mirror to charges. So our agenda includes the classic problem of the point charge above a grounded conducting plane. And of course, I'll briefly describe a point charge near a grounded conducting sphere. And there are many other possible situations. I'll just hint at them, but not discuss them. We'll encounter them in the home assignment. So advice is you will encounter many such situations which can be so easily be solved by such methods in your later profession as well. One has to be aware of this possibility. In problems, however, it's obvious in exam, from the point of view of exam, it is typically obvious when you are invited to use this method. Okay, so it is not like that you will not be able to know whether it is needed to be solved by method of images. Okay, typically it becomes clear from the way the question is formulated, but it's an important technique. So let's start with the point charge on an infinite grounded conductor. And as I say, it's a trick allowed by uniqueness theorems. Okay, so let's set up the problem. A point charge is held. This is a point charge. Okay, is held uh, by at a distance d from the infinite. I have shown it not only a plane, but it's actually an infinite plane. Okay, so this sort of divides the world into upper half and lower half. So lower half is shielded, okay, from anything because this is a grounded conducting plane. Okay, so our task is to calculate the potential everywhere. Of course, we know that if we can solve for potential, then everything about the electrostatics is really known. I can find out electric field, I can find out the energy, I can find out forces and things like that. So that is why we want to illustrate with this problem. Uh, so challenge is how much charge is induced. Of course, I expect that if I put a plus Q here, then there will be minus because the conductor, there will be electrons will be piling up here, there will be minus charges on the surface. The question is how much charge is induced and how is it distributed in the plane? Okay, that's the question that you want to answer. It's a hard problem otherwise. Okay, but you can see how easy it will become if we use the method of images. What is method of images? It looks like that if I put a minus q charge at minus d, okay, then I can see that the electrostatic condition for this infinite plane is not going to change. It will remain v is equal to 0. Okay, with that I state the problem. So solve Poisson's equation in the region. What is our region of interest? The region of interest is the upper half, z greater than 0. Okay, and the charge distribution is plus q. So that cannot be changed. So our solution has to solve for the boundary condition that v is equal to 0 at z is equal to 0 and q is at 0, 0d. And of course, the other boundary condition is that v will go to 0 if we go far away from the charge. Okay, either in the distance, if you go here, or you go in any, if you are going away from the plus charge, then it should become 0. So these are the two conditions. So the solution lies in the trick that consider an equivalent problem with an image charge placed at the opposite side of the conducting plane. Okay, there's a so minus q here, and I'm saying it's an equivalent because it's in the region of interest. Okay, and I cannot change, so I can put any image only in the region where it is not under analysis. Okay, so that satisfies all that. Okay, so let's do that. So let's put a minus q at 0 minus d, 0 0 minus d here. Okay, so why am I doing that? Because I know if I put a minus q here and plus q here, okay, then this perpendicular bisector between these two will still have v is equal to 0. So that is automatically satisfied. Okay, and what else I need? Okay, and v is going to be 0, so the boundary condition is satisfied, and I'm putting a charge which is not, I'm not in any way altering the region of interest, and hence this should work. So this is a solution. Okay, so if that is uniqueness theorem tells us that by placing minus q, if I can get the boundary conditions but both the boundary conditions are satisfied, my plus q is at where it is required, and hence this is indeed the solution. All right, so this is the, how much is the image charge? So we have ensured that the boundary conditions remain intact. Okay, so by putting a minus q at 0 0 minus d, so if charge distribution is the same in the region of interest and the boundary conditions remain the same, uniqueness theorem guarantees that the solution is right. So in this case, the solution is indeed right. Okay. Once I'm assured of that, I can simply write down Vxyz. Okay. That the method is so simple: plus q and minus q. So q x square plus y square z minus d square, and q is z plus d, because in the mirror d square. That's it. So once I know V, X, Y, Z, that's the solution. Okay. Of course, what use I? So it works because the induced negative charge gets mimicked by the charge exactly. Okay. Which means the presence of a minus q at a distance d away from the plane in the opposite direction completely mimics what happens to the conductor's surface. Okay. And hence I can now calculate sigma or whatever I want to. All right. So let's do that. So let's calculate the induced surface charge. So we know the V, so we can always calculate the, so how do I calculate that? I know V, I just wrote it down in the last slide. Okay, so sigma is of course in the, sigma is epsilon naught. We know that this is sigma by epsilon n, and that is nothing but the del V by del n in the opposite, in the normal direction. So minus epsilon del V by del n. Okay, so that is the boundary condition that we know. So since I know V, I can always calculate this, and that is simple in the normal direction. Normal direction is, in this case, is the Z direction, and hence the it is easy to differentiate. So that's why I get contribution only from the Z minus D here and Z plus D here, and then apply to Z is equal to 0. Okay, because I want to find out sigma at this plane, Z is equal to 0. As simple as that. So a little bit of simplification. Okay, if I do, then I get qd x square plus y square plus d square 3 by 2 minus 1 by 2 pi. So I've gotten sigma because I know V, and I applied the boundary condition that we know, that is applies to the conductor. Okay, so now we can proceed to calculate the total charge. So we know sigma now at all places. Okay, in x, y, z. So if I integrate this sigma over the whole plane, okay, then I can find out how much charge is to be induced on the plane. You can guess what will be, if I integrate, how much it should turn out to be. Of course, minus q. All right. So let's see if that happens. Okay. So total induced charge, let's figure out by integrating the surface charge over the whole plane. Okay. So sigma I know, I just found out. I have rewritten in terms of s square, s being the polar distance in the radial in the xy plane. Okay. So x square plus y square, I have replaced it by s square because I want to use the polar coordinates. Okay. In doing it, it's easy to do that for an infinite plane, for example. So what is the total q? Total q is of course sigma dA, and I can integrate from in the cylindrical coordinates or polar coordinates s ds d phi, phi going from 0 to 2 pi and s going from 0 to infinity. All right, that's a simple integral. Okay, so I worked that out. So I can write it down by 1/2 here, and instead of s ds, I write d of s square and pick up 1/2 here, and that is simple integral then, and qd s square plus ds square root over from 0 to infinity, and that is indeed minus q as one would expect. Okay, so why do I expect that? Because all lines of force emanating from plus q would finally end up at some minus q on this plane. Okay, and obviously this has to be then, the total charge has to be then minus q. Okay, so to check your intuition of field of lines, you can try drawing, okay, field of lines on this. Okay, so how will it look like? Will it look like an umbrella or a fountain, or how is the placing of the field lines occur? You please try that and check that your intuition is right for the field lines emanating from plus q and ending up in the grounded plane, okay, which has minus q on the whole induced on it. Okay, so let's look at the force on the charge. Okay, so how much is the force? Force can easily be computed. So this force is actually because of the charges, induced charges. But since it's an equivalent problem, I can directly write it down. Okay, so I don't have to do anything. Okay, not any component, integrate, nothing. Okay, so f is simply q square, and the distance between these two is, okay, 2d, so 2d square, so 4d square, and of course in the minus k direction. Okay, this is not k direction, this is, it'll keep attracting towards the plate, and so it will be in the minus k direction. Okay, I'm missing a minus sign here. Okay, so the charge is attracted towards the plane because the induced charge is minus q. So how about energy? Okay, so can I write down the energy as also the energy because of plus q and minus q? One has to be careful. That's not true. Why? Because energy is stored in the space. And remember, half the space is not available to me. This is occupied by the conductor. Okay, so only half the space is available for in fact, that is my region of interest. So it cannot be that the energy is stored by because of minus q. Minus q is only helping us trying to find out what happens in this region. So energy will be stored is only at z above 0. So this cannot be true. Okay, so what will be true is actually half of this. Okay, and so that would be minus, of course, okay, 1 by 4 pi epsilon naught q square by 4d, not 2d. Okay, just half of what we would expect only for a plus q and minus q, because half the world is not there in our region of interest. Okay, so we can always also calculate, we know f already. Okay, so we can always calculate the work done from going from minus and d to infinity. That's bringing the charge q from infinity and placing it at d. Okay, so it's a conservative force, so I can do f dot dl, and I just plugged in this f, and dl here is dz. I can bring it straight, because any method is possible for me to bring it down, and this is a straightforward integration. Okay, and that indeed gives me 1 by 4 pi epsilon naught q square 4 by d, which is half of this, which is the claim. Okay, so the best method is to actually find force, okay, and then do a line integral for the easiest path you have to calculate the energy stored. All right, so you need a little bit of care in interpreting contribution from image charges, what they can contribute to and what they cannot contribute to. Okay, the next simple example that classic example actually I'm going to do is a point charge in front of a grounded spherical conductor. And our task is to find potential outside the sphere and of course induced charge. So it's outside the sphere. That's the region of interest. Okay. So let's see, that's the diagram. So this is a sphere, grounded conducting sphere, and grounded is V is equal to 0. And I put a plus Q from the center at a distance A. Now the question is, can I use the image method? Okay, that is, the question boils down to, if I want to put an image method, it must be somewhere outside the region of interest, which is inside the sphere. Okay, so how much charge q prime can I put from what distance from the center such that q prime and q contribute and make sure that this potential surface remains zero. If that is there, then I've solved the problem, because plus q is in its place, and my region of interest is outside the sphere, and I have put a charge here such that this and this still make the boundary condition that is specified to me, that v is equal to 0. If I have done that, then I have solved the problem. So is this possible to do? Fortunately, it is indeed possible to do. Okay, because if I put a q prime, the question boils down to what should be the distance this b. Okay, the line between the center and this is a, and such that q prime and q contribute uh, contribute no potential here. Okay, so the boundary conditions must be for r greater than, we are remaining the same. There is a 200 BC theorem by a Greek, Apollonius, who discovered that the ratio of distances, okay, from two given points in fixed ratio, if you have, then the locus is actually a sphere. So we are sort of assured by a geometry. Okay, if I divide this line, okay, from two different points in some fixed ratio, okay, then the locus is the sphere. And this was realized by Lord Kelvin in 1848 for this problem. Okay, when at that time was not Lord Kelvin, he was at the age of 24. Anyway, assured by that, we now know that I can always find two quantities have to be figured out. There is b and q prime. Okay, and so, and I know that this locus would be v is equal to 0, so I choose 2 points, p1 and p2, and set up the potential and set it to equal to 0. I'll have two independent equations, and I have two unknowns to determine, and that should be simple. So at p1, this should be equal to 0, q prime method. Okay, at p2, it will be a q prime r plus b and q a plus r. Okay, that should be 0. So solve for q prime and b. That's easy to do. Okay, so if you do that, then q prime turns out to be negative of r by aq. Okay, so ra is larger, so this is a smaller q. Okay, and it is of opposite charge. And b, the distance from the center where I should put this minus charge, which is reduced by minus r by a, is r square by a, or ab is equal to r square. That's the relation. So once I found out this, then writing the potential for the charges is trivial. Okay, I can write down in terms of v, r, and theta, and please do that. Okay, now you can solve for v, r, theta, and then you know from boundary condition how to find out induced surface charge. You can find out the force on this charge. Okay, and you can find out the energy exactly as we did for the infinite plane, except that the symmetry of the sphere is here. All right, so please do so. Okay, so let me then give my concluding remarks. So method of images is a very powerful method sanctioned by uniqueness theorems. All we need to take care is that the conditions for validity of uniqueness theorems are satisfied. Okay, if your image charge is attempting to somehow, while doing it, to the domain of interest, then it will not work. Okay, you cannot change the original Poisson problem with the boundary condition or the charge distribution. Okay, sometimes while using mirrors, the images get reflected back into the region, then of course it will not work. Okay, there are many practical problems that are easily solved by this technique. You will encounter them in your own profession as an engineer. A charge near a grounded conducting body is actually everywhere, ubiquitous in the laboratory and in practical uses. Some ground is a metal is there which is grounded, and you are bringing a charged object there. Okay, so those methods are to the first level can easily be calculated by image of methods of images. All right, but there are many methods of solving which are sort of techniques. Okay, and specially sanctioned by uniqueness theorems. But in this course, this is the only real spatial method that we study. Okay, there are other techniques which requires maths. Okay, in section 3.3 of the book, we are not doing it in this course. Okay, so section 3.3, special techniques to solve separation of variables and so on. This will be this you will learn in maths. Okay, and then you will be ready for that, and but not in this course. Okay, we'll have some interesting problems in the home assignment on method of images. It's a very popular method, and you better master this technique as much as possible.